Welcome. In this video, we are going to introduce atomic structure in terms of electron configurations. So this is something that fits within topic 1.5. And the first thing I want you to stop and consider is that when we study the atom in chemistry, we tend to focus more on the electrons than the nucleus. Why do you think this is? The reason why is if you look at the atomic structure, the protons and the neutrons are in here in the nucleus, and the electrons are out here on the outside. So the electrons are what are interacting with the surroundings. So the electrons and the structure of those electrons determines the properties. It determines how these atoms bond. And so the electrons have to do with all sorts of interesting chemistry that we observe. So we tend to focus more on them than what's going on inside the nucleus. So we want to know more about the electrons so we can understand how atoms behave. And so we're going to start by refreshing some knowledge that we might have from first year chemistry. So some ideas about electrons we have maybe at this point would be that electrons exist in these things called shells that surround the nucleus. And you may have heard of the idea of electron clouds as well, but we probably didn't get into much detail about what that is. And then protons and neutrons are in the nucleus at the center of the atom. You might remember some patterns, some useful information that you can get from the periodic table. The row number that an element is in will tell you how many shells are in the atom, and then the column number will tell you how many electrons are in the outermost shell. Those are called valence electrons. So I could look over here, iodine, and say, oh, it's in row 5, so it's got 5 electron shells, and since it's in column 7, it has 7 electrons in its outermost shell. And then you might remember seeing visuals that look like this, where you had some sort of sense that different shells can hold different numbers of electrons, but we might not be entirely sure why. So the first shell held 2, the second held 8, the third held 18. So those are some things you might remember from regular chemistry. So let's kind of dig into this more, what's going on with the electrons. So one question we want to answer is, why do different shells hold different numbers of electrons? And that is because these electron shells are actually divided into something called subshells. So this visual on the left I really like because it shows the kind of zoomed in version of it. So what we thought of as the first shell is made up of one subshell. The second shell is broken down into 2 different subshells. The third has 3 different. The fourth has 4 different subshells. And you see in this visual they're color coded, and there's these letters over here to the side. So we use letters S, P, D, and F to distinguish these different subshells. We can go even further and say, well, what are subshells made of? Subshells are made of orbitals, and orbitals describe the possible energy and location of electrons. And excuse me, what I was going to show you is in your OneNote, if you are interested in looking into this more, you can look on page 10C. It has some pages that has to do with quantum theory. There's text references, there's videos, so there's stuff you can look at in your OneNote. But we're not going to go over it in detail in class because we're not really tested on this in detail in the AP exam. So for right now, we're just going to say there's these things called orbitals. They describe the location of electrons. Different orbital types correspond to different shapes. So we saw these letters, S, P, D, F. And some things about them is for the S type, there's only one orbital and it's a spherical shape. The p orbitals, there's 3 of them, and they have these kind of dumbbell type shapes. So the d orbitals, there's 5 of them, and then the f orbitals, there are 7 of them. So you might notice a pattern here, 1, 3, 5, 7. They have different numbers of orbitals, they're different shapes. Don't worry about memorizing the shapes, that's not important. So to summarize what we know here, electrons exist in orbitals. It turns out each orbital can hold up to 2 electrons in it. A subshell is just a collection of orbitals with the same energy. And then a shell is a collection of subshells with a similar distance from the nucleus. So why only two electrons? That has to do something to do with something we call spin. So there's one more level of detail we can get to with electrons. So we can say which orbital an electron is in, and then we can also describe a property that we call spin. And if you're wondering where this concept of spin comes from, it has to do with the idea that you may have heard of in physics, if you've taken physics before, that a spinning charge will generate a magnetic field perpendicular to it. And this is something that we observe with electrons, is we have observed this kind of magnetic field. They somehow react to a magnetic field. So we say that these electrons are behaving as if they're spinning around in a circle. And we observe that they can have two different, directions of this magnetic field. So we say that the electrons have two different possible spins. We call those spin up or spin down. And again, I'm really glossing over this. If you want more detail about the idea of spin, you can refer back to that page I was just showing you with quantum theory notes. And I've got some videos in there too that go into it. So some things we should know about spin is that two electrons in the same orbital must have different spins. And we will write something like this down here. We call these orbital diagrams to show where the electrons exist within atoms. And with these orbital diagrams, we use arrows to represent electrons. And each electron is an arrow, and those arrows will either point up or point down to represent, they can have either spin up or spin down. Okay, so to summarize, where do electrons exist? They exist in shells. We describe shells using these whole numbers, 1, 2, 3, 4. These shells are actually broken up into subshells. So there's S, P, D, F. We use letters to distinguish those. And I should also say we use different types of vocabulary for it. Sometimes we call these shells energy levels. And we might call subshells sublevels. Put that vocab out there. And then these subshells are made up of orbitals. An S subshell has 1 orbital, P has 3, D has 5, F has 7. Here's what they look like. You don't need to memorize the shapes, don't worry about that. But we do need to know is each orbital can hold 2 electrons. So as a result, with the S type of orbital, there's only one orbital in an S subshell, so it can only hold 2 electrons. The P's have 3 orbitals, so 3 times 2, they can hold 6 electrons. The D's have 5 orbitals, 2 electrons in each. That means they can hold up to 10 electrons in them. And then there are 7 F orbitals, 2 electrons in each. That means they can hold up to 14 electrons max. All right, here's another page just visualizing the different electron locations. Notice how we only go up to shell 4 in this example. That doesn't mean that that's where things stop. If you look at the periodic table, the heaviest element on there right now has electrons in 7 shells. So we have 7 rows right now. And it could, in theory, keep going. How they fit together. So if we were to actually, visualize a more accurate visualization of what the electrons are doing, it might look something like this. So just acknowledge that when we usually write out these, our atomic model, we often use the Bohr model, which represents these electrons being in these shells. And that's something that's easier to visualize, and it is useful because it's a little simpler for us to look at. But we just want to acknowledge that this right here is more accurate, and this is a better representation of those electron clouds, which you may have heard people mention in regular chemistry. That's what these orbitals are, is these clouds, these probability density clouds. And again, if you're interested in more like what is she talking about probability densities, then I encourage you to read more in your textbook or watch the videos about quantum theory. Okay, so we want to be able to describe where the electrons are in an atom. And to do that, we want to be able to draw an orbital diagram and write electron configurations. So here's an example of what an electron configuration looks like. This is something that tells us how many electrons are in the subshell. And then an orbital diagram gives us a little bit more information. It shows us the orbitals and the spin of the electrons. When we're writing these, there are 3 rules that we need to follow. We're trying to figure out where the electrons will go. So let's go over these. Rule number 1 is that electrons will fill orbitals in order of increasing energy. The orbitals of lowest energy will fill first. So what does that mean? Well, in general, the low energy orbitals are closest to the nucleus. So here's a visual showing these orbitals with respect to the nucleus. Remember, the nucleus is positive. That's where the protons are. And the lowest energy orbitals are the ones that are closest to the nucleus. And that makes sense because electrons are negative, right? And opposites attract. So these electrons are going to be attracted to the nucleus. So they are going to want to be as close as possible. Okay, so electrons are going to fill the closest orbitals first. That's rule number 1. Rule number 2, if you are filling a subshell that has multiple orbitals available, like for example, if you're looking over here at 2p, there's 3 different orbitals available here. You're going to put 1 electron in each orbital before you start to pair them up. When you do that, unpaired electrons in adjacent orbitals need to have the same spin. Rule number 3, if electrons are in the same orbital, they must have opposite spins. So this isn't going to make much sense until we apply it. So let's look at a sample one. Let's look at oxygen. And what we're going to do first, we're going to look at the periodic table. And oxygen looks like this on the periodic table. Here's its little box. The number down here at the bottom, it's the mass. We're going to ignore that for right now. It's not relevant to what we're doing. On the top here, this is the atomic number, which is the number of protons. And when the atom is neutral, if you have a neutral atom, the number of protons equals the number of electrons. The positives and negative charges are equal. So what this means, if we have a neutral atom of oxygen, then it's going to have 8 electrons in it. And neutral just means it's not an ion, it's not charged. Okay, so we've got 8 electrons, and here's our kind of map, our visual of the atom. And if we look at our rules here, rule number 1 is that electron's going to fill the lowest energy orbital first. So my first electron is going to go down here in the 1s. And each arrow represents an electron. Let me write that down. So each arrow is 1 electron. So my first electron is going to go in the 1s. And it doesn't matter which way you draw this arrow initially. You can point it up, you can point it down. Doesn't matter. Okay, my second electron also wants to be as close to the nucleus as possible. In order for it to be in the same orbital, though, I gotta go with rule number 3, it has to have an opposite spin. So if my first arrow pointed up, my second arrow is going to point down. Okay, now this orbital is full. All right, my third electron, remember there's 8 electrons that I'm going to be placing here. My third electron still wants to be as close to the nucleus as possible. But the 1s is full, so it's going to go the next closest, which is the 2s. The fourth electron is also going to go in the 2s, but with an opposite spin. Now this orbital is full. Okay, now we're at my 5th electron. The 5th electron can't go in the 1s, can't go in the 2s, so it's going to go the next best option, which is the 2p. The 6th electron is where it gets interesting, and we have to apply this rule right here. So when you have multiple orbitals available, you're going to put 1 electron in each orbital first before you start to pair them up. Excuse me. So the 6th electron, rather than being in the same orbital as the 5th one, it's going to go in the adjacent orbital. And it's important to think about why this might be. So some things we know about electrons is that, and just charge in general, is that electrons are negative and opposites attract. So electrons and protons are going to attract. So that means electrons are attracted to the nucleus. So they want to be as close to the nucleus as possible. Okay? But we also know that like charges repel. So 2 electrons, they have the same charge, they're going to want to repel each other. So it makes sense that they would be in separate orbitals. They're going to want to kind of stay as spread out as possible there. So these 2 electrons are going to be in adjacent orbitals. So that's 1, 2, 3, 4, 5, 6. My 7th electron is also going to go in its own orbital. So there's orbitals available of equal energy. They're going to put 1 in each before you start to pair up. Also notice what I'm doing here is notice how I'm drawing them all pointing up. So unpaired electrons in adjacent orbitals have the same spin. So you should draw them all pointing up or draw them all pointing down. Okay, so that's 1, 2, 3, 4, 5, 6, 7 electrons. My 8th electron, now we don't have any more orbitals for it to be in by itself, so now it's going to pair up with this other electron. And so even though these, two opposites, sorry, these two charges repel each other, these two electrons repel each other, basically the attraction to the nucleus is kind of like winning out, So this electron's saying, oh, well, I want to be close to the nucleus, so that's fine. I will pair up with this other electron and hang out there. And this is important because I think that we, from regular chemistry, might get the sense that electrons want to pair up, like that electrons attract each other. And it's important to keep in mind the electrons are actually negative. They actually repel each other. So the thing that actually causes them to pair up, it more has to do with their attraction to the nucleus. So it's not that they want to pair, it's more that they're willing to pair up in order to be as close to that nucleus as possible. So that's just a little kind of shift of your frame of reference that we'll maybe get back to when we get into bonding. So, okay. The tricky part when we're writing these is how do you know the order of increasing energy? So right now when you start out practicing, you might want to use this visual to help you figure this out. But, on the AP exam, typically you're not going to have your notes to look at, right? So you're not going to have this visual to look at. So how do you figure this out? Do you need to memorize this? Well, it turns out there's a pattern that corresponds to the periodic table. And if you look right here, this kind of lays out the pattern here. And it's really cool because this is some very strong evidence that there's a relationship between electrons and the physical and chemical properties of elements. Because if you think back to when they first made this periodic table, this was before we had quantum theory and knew about, S and P subshells and orbitals and stuff. All they knew was what they observed about elements, their properties. And they started organizing these elements based on observed properties. And it turns out that there's a relationship between those observed properties and where the electrons are. So that's really cool. So this periodic table, it lines up with elements with similar properties, and it also totally matches with the subshells and orbitals where your electrons exist. So how we might use this pattern is, let's say we want to write the electron configuration of the element titanium, okay? If you look at your periodic table, titanium's right here. 47.7. Okay, this is what it looks like. Boom. So what you would do is you would basically read your periodic table as kind of like a map for where the electrons go. So titanium has 22 electrons. We want to figure out where all 22 of those electrons go. So if you look on your periodic table, this is element 1, this is element 2. Notice they're both in the section labeled 1s. So the first 2 electrons are going to exist in the 1s subshell. All right, elements 3 and 4 are here in this section labeled 2s. So my next 2 electrons are going to go in this 2s subshell. And if you keep counting, you notice it goes across 5, 6, 7, 8, 9, 10. And notice how this is 6 elements wide. So there's 6 electrons that are going to go in the 2p. And then elements 11 and 12 are down here. That is the 3s. And then over here, elements 13 through 18 are here in the 3p. So that's 6 electrons that are going to go in the 3p. And then 19, 20, the next 2 electrons go in the 4s. And then the last 2 electrons, 21 and 22, they go in the 3d. So it's really useful to learn this pattern and use it, because you notice there's some weird things about the filling pattern. If we go back to this visual right here, notice how you go 1s, 2s, 2p, 3s, 3p, and then 4s comes next, and then 3d, and then 4p, then 5s, then 4d, then 5p. So it's kind of a weird pattern here, right? It might not be intuitive, but we can use this periodic table to help us see this pattern here. So you want to use this the first few times you're trying to figure out electron configurations, and then you'll find that you won't need to look at these labels anymore because you'll start to notice patterns, which I will point out to you right now. So the 2 main kind of patterns you want to notice, one is that the width of the block is the number of electrons. So we refer to this over here as the S block, and notice that it is 2 elements wide, and S subshells can hold 2 electrons. Over here, the p block is 6 elements wide, and then we know that p subshells can hold 6 electrons. And then here in the middle, the d block is 10 wide, it can hold 10 electrons, and the f block is 14 wide, it can hold 14 electrons. And the reason for that goes back to, excuse me while I flip back through some slides, goes back to this right here, the number of orbitals. So S is one orbital, that's 2 electrons. P has 3 orbitals, 6 electrons. D has 5 orbitals, that's 10 electrons. F has 7 orbitals, that's 14 electrons. Okay, so here's where we're. The other pattern you want to notice is you can use the row number to predict what shell they're in. So notice for the S and P's, the shell number is equal to the row number. So third row is 3S and 3P. For the D block, the shell number is the row number minus 1. So like in the fourth row, you're filling up the 3D. In the fifth row, it's the 4D. The sixth row is the 5D. For the F block, it's the row number minus 2. And you might think, wait, the F block isn't even in the periodic table. But if you follow the numbers down here, like in row 6, it goes like 55, 56. And then it goes down here, like you've got your like 57, 58, they're actually down here. So it goes whoop, and it kind of continues on in the little block below. Technically 57 goes here, 58 goes here. It gets a little confusing. But basically, this right here belongs right in this section of the periodic table. We just show it below just to make the periodic table easier to look at, so it's not super wide. So these up here belong in rows 6 and 7. Okay. So overview, draw an orbital diagram. Put electrons in the lowest energy orbital first. So follow that pattern using the periodic table. 2 electrons per orbital max. If you have 2 electrons in the same orbital, they must have opposite spin. And if you have orbitals of the same energy available, you put 1 in each first before pairing up. So on your note sheet, what you want to do next is on page 10A, you want to try some of the practice problems and complete the orbital diagrams and electron configurations. So take a moment to grab that page if you haven't yet and try it. So pause the video, and then I'm going to go over a couple of the answers. So pause the video, try it, and then you can check your work with some of these ones. Okay, so the first one, if we have 1 electron, it's going to go in the lowest possible orbital. So the orbital diagram might look like this. You could use a box or a line, whatever you would like, works. You could also draw the arrow up or down. So these are all acceptable variations for orbital diagram. The electron configuration is 1s1. All right, that second electron is also going to go in the 1s. So your orbital diagram would look like this. Your electron configuration would be 1s2. All right, now let's skip to one with more electrons here. And notice how I copied and pasted the filling order. So you might find that useful when you're first doing practice, is to paste these next to practice problems so you can see them. And then you'll find that after doing a few of them, you won't need this, and you should just be looking at your regular periodic table that the College Board will give you. Okay, so carbon has 6 electrons. And if we follow our pattern here, the first 2, they're going to want to go in the ones close to the nucleus first. So first 2 go here. Third electron goes here. Fourth electron goes here. Fifth electron goes here. Sixth electron goes here. So what I do is it'd be 1s. So it looks like this. 2s. And then 2p should look like this. They can either both be facing up or both facing down. That doesn't matter. The electron configuration would be 1s2, 2s2, 2p2 for carbon. All right, let's try one more. Okay, germanium, 32. If you look on your periodic table, germanium is right over here. It's right there, so it's in the 4th row over in what we call the P block over here. So I'm actually going to do the electron configuration first. Sometimes it's easier to do that first. So I'm just going to follow my pattern. So I'm first going to go the 1s. Okay, and then I'm going to go down to the 2s. What comes next over here is 2p. Then I'm going to drop down, I get to the 3s. Work my way across, now I'm in the 3p. Drop down, what comes next is the 4s. What comes next is the 3d. And then where I end is I'm 2 sections in, like 2 elements in the 4p. So that tells me I've got 2 electrons in the 4p. So what I'm going to do now is I'm going to translate this into an orbital diagram. And however you organize this in terms of like spacing is fine with me. You just need to label what they are. Okay, then 4s, and then 3d has 1, 2, 3, 4, 5, and then 3p, 4s, 3d, 4p. Okay, let me make sure okay, 1, 2, 3. All right, 2 electrons here, 2 here, and then these are all full. And this is where you can see sometimes people use these actually half arrows because they get lazy drawing the full arrow. That's fine. Okay, so this is our half arrow method. For S, I've got 2 there. Then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we got these ones right there. So we end up with 2, these are what we call unpaired electrons. So we'll talk about that in the next video here with paired versus unpaired electrons. All right. Thanks for watching. Hope this helped. Email me if you have questions.